What I want to do here is, it's this question that has come up, which is calculate the speed of an alpha particle. And let's just look at the alpha decay reaction for a start. We've got a fairly common one where we've got the uranium-238 and it breaks down to give you the thorium-234 with 90 atomic number plus your alpha particle, which is there, plus we get our energy, which is 4.25 mega electron volts. This is not the only speed for an alpha particle. There are some different reactions, I think. But, you know, if I just give that to you and say, we'll calculate the speed, you've got to have a little think of the process. Remember that if this guy in its frame of reference had a zero velocity, then afterwards, these two guys, if this energy is released as kinetic energy, then these two guys have both got velocities, and for conservation of momentum to hold, they must be going in opposite directions, not equal and opposite velocities, because they've got different masses. But so we need conservation of momentum to hold, and we need this much energy produced. And so there's a few things going to come out of this for their conservation of velocity to hold. Well, let's just have a look. If this one's mass, well, we'll look at the masses first. Thorium's mass, we'll take it 3.887 times 10 to the minus 25. Quite a big mass because it's got all those particles, 234 of them, or nucleons. Helium, we've got 6.66 times 10 to the minus 27, quite small. So if we divide those, we come up with a ratio of 58.36. So the masses are in those ratios. You know, helium's mass, thorium's mass divided by helium's mass is equal to 58.36. Now we know for conservation of momentum to hold that we're going to have to get the proportion of the velocities right, because thorium's mass times its velocity, so the mass of thorium times the velocity of thorium must be equal to the mass of helium times the velocity of helium. So for those two little guys to hold, we can say that the V1 over V2, or the velocity of thorium divided by the velocity of helium is equal to the mass of helium over the mass of thorium. So we can see those little relationships at work. And so if we know that, we can then write out an equation for the energy. We've now got the relationship between the velocities. So if we're looking at the alpha, it's going to have a velocity which is 58 times more, right? Or 58.36 times more. So let's write out our equation. So 1/2 mass of the alpha, let's just make sure we do this correctly, mass of alpha times velocity of alpha squared. All right, so that's our alpha. That's its kinetic energy. It's got a mass of alpha, it's got a velocity of alpha. Now we know it's got 58 times the velocity of thorium. So let's now do our thorium's kinetic energy. We're going to do this all in terms of velocity of alpha because we want the velocity of the alpha particle right up there. So if we now do the thorium's got a mass which is 58.36 times the mass of alpha, right? And its velocity is 58.36 times less. So those two things must add up to the energy, right? Added up equal the energy, which is 4.55 mega electron volts. This is the guts of this question, right? Is saying that the conservation of momentum means we've got the helium particle moving 58.36 times faster, which means that when we do the velocity of the thorium, we have to divide it by 58.36 because we're doing this all in terms of the alpha, and that the mass of the thorium is that much times bigger. So kinetic energy of, this is EK for thorium, EK for helium. And the two of them must add up to that because that was the energy released. So after doing a little bit of cancelling and that sort of thing, what we can end up with is an equation, what we have to do is a couple of things to remember. Convert your electron volts back into electron volts, not mega electron volts, and then convert them back into joules, which means you're going to have to times by the charge on electron. So don't forget to do that. You can see what's going to happen here. We've got that one's going to cancel with that one. This will end up being, that will get rid of, that'll be that squared, right? And you just have to divide by 58.36, having cancelled with that. We can multiply that side by 2, that side by 2, that gets rid of the half. We can then divide this side over here by the mass of an alpha particle, which we had up here, and put the whole thing in, and we end up with this equation, which is 2 times 4.25 times 10 to the 6 times charge on electron, all divided by mass of the alpha particle, and we end up with it being equal to 1.429 times 10 to the 7 meters per second, which if we divide that then by 3 times 10 to the 8 speed of light, we end up with 0.047, or approximately 5% C. And we've worked out the speed of an alpha particle. Well done us.